Imagine, like, pushing a single line of code that accidentally exposes, I don't know, 1 million customer credit card numbers.
Oh, man.
Right. And all because a newly integrated AI assistant was granted just, like, a little too much database access. I mean, it is the ultimate nightmare scenario.
It really is. And in modern data environments, the line between a brilliant cutting-edge feature and a total catastrophic breach is, well, it's razor thin.
Yeah, totally.
And navigating that line requires a very specific, deeply integrated set of skills because you aren't just writing queries anymore, right? You are orchestrating this living, breathing digital ecosystem.
Which is exactly why you are here with us today. Welcome to the Deep Dive, everyone. Our mission for this session is simple. We are delivering a comprehensive masterclass and a full practice run for the DP-800 exam.
That's right.
So, if you are prepping to validate your data and AI skills, you have found the right place.
What?
We are going to tear down the concepts so you truly understand the logic behind them.
But before we jump into the technical weeds, let's establish the foundational rules of engagement for the DP-800 exam, just based on our source material.
It's a good idea.
So you have a strict 100-minute window to tackle between 40 and 60 questions. The exam is delivered in English, and you need a score of 700 to pass.
And from what I understand, you can't just, rely on standard multiple-choice testing strategies here, right?
Oh, far from it. The format is a heavy mix. I mean, you will see multiple choice, sure, but also multiple response, drag and drop, build list, active screen interactions, and even complex multi-layered case studies.
Okay, let's unpack this. We have 10 highly specific practice questions to get through today. But before we get to the flashy AI integrations, our underlying data logic needs to be bulletproof. So let's look at the bedrock, which is dealing with messy human-entered data.
Yeah.
Here is question 1. It reads, your data cleansing pipeline needs to identify duplicate customer records where the names might contain minor typographical errors or slight spelling variations. Which native database capability should you employ to quantify the similarity between these text fields?
Okay, classic problem.
Right. And to solve this, the exam gives us 4 routes. Option A, full-text search catalog indexing. Option B, standard pattern matching operators. Option C, semantic vector embeddings. Or option D, built-in string distance algorithms.
Right.
So my instinct here, just as a developer, is to use standard pattern matching, like a SQL-like operator. So I would lean toward option B.
Yeah, and honestly, that's a really common instinct, but pattern matching is just far too binary for this specific problem.
Oh, so?
Well, a like operator either matches the pattern or it doesn't. There's no in-between. And what's crucial in the prompt is the requirement to actually quantify the similarity of a typo.
Ah, quantify.
Exactly. And that points us directly to the correct answer, which is D, built-in string distance algorithms.
Okay, so if I misspell Smith as, Smith with a Y, a pattern match just straight up fails. But a string distance algorithm actually calculates the gap between them.
You nailed it.
Yeah.
Yeah, algorithms like the Levenshtein distance, they mathematically calculate the precise number of single character changes, so insertions, deletions, or substitutions, that are required to turn one string into another. It gives you an actual numerical similarity score.
Oh, wow.
Yeah, think about merging critical healthcare records. You need to know exactly how close 2 names are before just combining them.
Right. And what about the other options, like A, full-text search?
So A is great for finding a specific word buried inside a massive PDF document, but it doesn't give you that granular typo score we need here.
And C, semantic vector embeddings. That measures the underlying meaning of words,
Yeah.
right? Not mechanical spelling differences.
Right. Vectors really don't care about typos at all. They care about concepts, making D the definitive choice.
Got it. Okay, so we've cleaned up the typos. But cleaning data is really just the setup. Now we have to analyze it over time.
Exactly.
So imagine you need to track how those customers are actually spending money. This leads us directly to question 2. It asks, you need to calculate a moving average of sales over the past 30 days for each individual store without grouping the final result set into a single row per store. Which querying technique is designed specifically for this type of calculation?
Okay, pay attention to that wording.
Yeah, and the options are A, applying windowing functions with a defined preceding frame. B, utilizing correlated subqueries nested within the select clause. C, creating recursive common table expressions. Or D, implementing a cursor to iterate and aggregate row by row.
Right, so...
Actually, wait, I have to push back on the options here. If I want a 30-day moving average, why wouldn't I just write a traditional program to iterate using a cursor, like an option D?
Yeah.
Just look at the last 30 days, calculate it, and move to the next row.
I get why you'd think that, but in a production database, option D is a complete performance nightmare.
Really?
Oh, absolutely. Cursors process data sequentially, row by agonizing row. And relational databases are built to be optimized for set-based operations, not row-by-row iteration. Plus, the key phrase in the question is, without grouping the final result set into a single row.
Right, okay.
And that immediately rules out standard group P by Y clauses and points us to the correct answer, which is A, applying windowing functions with a defined preceding frame.
So window functions let you perform calculations across a related set of rows without actually collapsing your result set.
Yeah.
Like you still get to see every individual transaction row, but with an extra column showing that 30-day rolling average right next to it.
That is exactly the magic of it. By defining a frame, literally writing syntax like rows between 30 preceding and current row, the database engine handles the rolling calculation incredibly efficiently at scale.
Wow, okay. And what about option B, the correlated subqueries?
If you tried option B, the engine would execute a separate standalone query for every single row in your table.
Oh, yikes.
Yeah, which would bring your system to an absolute crawl. And option C, recursive CTEs, those are meant for navigating hierarchical data, like, say, a company org chart, not for calculating rolling averages.
Okay, that structural efficiency is definitely vital. But, I mean, brilliant analytics mean nothing if your environment isn't locked down.
Very true.
We have to secure this ecosystem, which brings us to question 3. When configuring an AI-assisted development tool to connect securely to your database environment, what is the primary security consideration regarding the tool context protocol?
Important one here.
For sure. The options are A, ensuring the AI model is deployed in the same geographical region as the database. B, restricting the endpoint connection permissions to the principle of least privilege. C, encrypting the natural language prompts using symmetric keys. Or D, disabling all database firewalls to allow seamless model interaction.
Wow.
I think we can safely laugh option D out of the room, right? Like, disabling firewalls for seamless interaction is a great way to lose your job.
It is the definition of a catastrophic decision. Yeah, please don't do that. The correct answer here is B, restricting the endpoint connection permissions to the principle of least privilege.
So why does that trump the other security measures?
Because an AI tool is essentially an external agent acting autonomously on your behalf. The principle of least privilege dictates that this tool should only ever be granted the absolute minimum access required to do its specific job.
Makes sense.
So if it only needs to read schema definitions to, like, help developers write queries, it must not have permission to delete tables or read the actual data within them.
Okay, so what about A, the geographical deployment?
That's a compliance issue, really, not a fundamental protocol security concern. And option C, encrypting prompts, well, that's natively handled by HTTPS in transit anyway. It's not the primary database access issue we're worried about.
Okay, so securing an AI tool is one thing. But how do you secure an environment against your own development team?
Good question.
Let's test this with question 4. In an automated continuous integration pipeline for your database project, you must ensure that modifications applied directly to the production database are not overwritten by older code in the repository. Which process is responsible for identifying these discrepancies before deployment?
All right.
Are we relying on A, code compilation validation, B, automated unit testing, C, schema drift detection, or D, pull request approval workflows? So what does this all mean for a developer's daily workflow?
It means confronting the reality of emergency hotfixes. Imagine it's Black Friday, right? The checkout system crashes, and an engineer logs directly into the production database to alter a table and fix the bug.
Which they probably aren't supposed to do.
They definitely aren't supposed to bypass a repository, but, emergencies happen.
And when they do that, the production database kind of drifts away from the official blueprint stored in your source code.
Exactly. So if you blindly deploy the old code the next morning, you overwrite the hotfix and crash the system all over again. Precisely. Which makes C, schema drift detection, the correct answer. This process actively compares the target database schema against the source control schema. If they don't match, the automated deployment just halts and flags the discrepancy.
That's a lifesaver. And A, compilation validation.
That just checks if the code is syntactically correct, not if production has changed. Option B, unit testing, just checks data logic. And option D, pull requests, well, those rely on humans reviewing new code, but they have zero visibility into live manual production tweaks.
Schema drift detection is the ultimate safety net then. Okay, so the back end is secure from rogue code, but what about the presentation tier?
Right.
We need to protect the data right as it reaches the user. Here is question 5. A customer service application connects to the database using a shared service account. You need to ensure that call center agents using this application cannot view full credit card numbers, but the application's underlying queries should not need to be rewritten. Which security implementation handles this at the presentation layer?
A very common real-world scenario.
Yeah. We have 4 choices. A, applying column-level cryptographic encryption. B, implementing strict row-level security predicates. C, enforcing application-side authorization logic. Or D, configuring dynamic data masking rules.
Okay, so the crucial constraint in this prompt is that we cannot rewrite the underlying queries.
All right.
That strictly eliminates several options right off the bat, leaving D, configuring dynamic data masking rules, as the correct answer.
I always think of this like a magic mirror. Like every user is looking into the exact same mirror, meaning they are running the exact same database query, but depending on who is standing there, the mirror reveals something completely different.
Oh, I like that.
Yeah, so a floor manager sees the full credit card number, but the call center agent just sees like a bunch of X's and the last 4 digits.
That analogy perfectly captures the mechanism. Dynamic data masking happens right at the presentation layer, dynamically obscuring the data as it's handed back to the user. The data on the disk remains entirely untouched, and the query itself never changes.
Awesome. And if you chose A,
With A, column-level encryption, you would physically scramble the data on the disk, and that requires rewriting the application to manage decryption keys, which violates our prompt.
gotcha.
B, row-level security, is designed to hide entire rows of data like hiding a VIP customer, completely not specific columns within a row. And C, application-side logic, directly violates the prompt by forcing developers to rewrite the application CAD.
Okay, so we have clean data, and it is fully secured from the disk to the presentation layer. Now, the modern front-end engineering team wants to connect to it.
Naturally.
Question 6 tackles this. You are integrating your database with a modern front-end application that requires flexible data fetching, allowing the client to specify exactly which related entities it wants to retrieve in a single request. Which technology native to the Azure database ecosystem provides this capability out of the box?
All right, what are our options?
Is it A, exposing database objects through a GraphQL endpoint? B, creating traditional RESTful application programming interfaces? C, building custom webhooks triggered by database events? Or D, utilizing bulk data export operations via blob storage?
Well, front-end developers constantly battle 2 extremes: overfetching, where they get way too much data, and underfetching, where they have to make a dozen different requests just to load one single web page.
Right.
The technology engineered specifically to solve this is A, exposing database objects through a GraphQL endpoint.
Because with a REST API, which is option B, if I want to load a user profile, I had to hit one endpoint for their name, another for their order history, and a third for their shipping status.
Exactly.
And on a weak mobile connection, that latency just crashes the app.
Yeah.
But with GraphQL, the client application basically sends a highly specific shopping list.
That's a great way to put it. The client dictates the exact shape and scope of the data it needs in one single precise query. Option C, webhooks, are entirely backwards for this. They are for pushing event notifications outward, not querying data inward. And option D, bulk exports, is for massive asynchronous data dumps, not real-time application fetching. GraphQL handles this natively.
Okay, here's where it gets really interesting. The front end is connected smoothly, but modern users don't just want exact keyword matches anymore. They want to search by meaning. Welcome to the AI era.
Here we go.
Let's look at question 7. When preparing text data for semantic search within the database, the raw text must first be converted into a mathematical representation. What is the correct terminology for this numerical array that captures the semantic meaning of the text?
Okay.
Your options are A, a vector embedding,
Yeah.
B, a cryptographic hash, C, a relational foreign key, or D, a full-text inverted index. I mean, if I'm building a traditional search engine, I'm using option D, an inverted index.
Right.
But that's just a giant glossary. If a user searches the word joyful, an inverted index won't show me documents that only contain the word happy because it only looks for exact letters.
Which is exactly why traditional indexes fail in AI applications. The correct answer is A, a vector embedding.
Yep.
To really understand semantic search, you have to realize we're mapping concepts into a high-dimensional mathematical space. A vector embedding converts a paragraph of text into a long sequence of floating point numbers. Words that share conceptual meaning like happy and joyful will end up mathematically close together in that space, even if they share 0 letters.
That makes the other options obviously wrong in this context.
Right?
B, a cryptographic hash is designed so that the slightest change in text creates a wildly different output, right?
And it's
For security verification, not finding similarities.
Exactly.
And C, a foreign key, is just a structural link between relational tables.
Yeah, vectors are the fundamental unit of meaning in the AI era.
But what happens when you have too much meaning? Imagine feeding an entire 500-page technical manual into an AI.
Oh, that's a mess.
That brings us to question 8. You are processing large technical manuals for an AI search solution. Feeding entire documents into an embedding model yields poor search precision. Which data preparation strategy improves semantic retrieval accuracy for long documents?
Right.
Do we use A, translating the document into a single universal language, B, splitting the document into smaller, logically coherent segments, C, extracting only the capitalized nouns and verbs, or D, compressing the text using standard lossless algorithms? I might guess compressing it, like option D, just to make the file smaller. Or maybe extracting the nouns, option C, to save space.
Yeah, but if you try D, a lossless compression algorithm, like creating a zip file, you turn the text into binary gibberish that the embedding model cannot read at all.
Oh, right.
And if you try C, extracting only nouns and verbs, you destroy the sentence structure and context that the AI actually relies on to understand the actual meaning. The solution is splitting the document into smaller, logically coherent segments.
It's like asking someone to read a massive encyclopedia and then demanding they summarize a single specific fact from it in one breath. The nuance gets completely washed out.
Yes, exactly. The industry term is document chunking. By breaking a massive manual down into distinct paragraphs or chapters, each chunk gets its own highly focused vector embedding.
Okay, that makes sense.
So when a user queries a specific error code, the AI can retrieve the exact paragraph that solves it, rather than just pointing at a 500-page manual. Option A, translating the language, obviously does nothing to solve the length constraint. Chunking is the only viable path.
So we've prepped our data perfectly. But what happens when you need to merge different types of search logic together?
It gets tricky.
Yeah. Question 9 sets this up. Your application combines results from a traditional keyword search and a modern semantic search. Since these two systems use completely different scoring metrics, which algorithm should you implement to mathematically fuse and re-rank their separate result lists into a single unified output?
Let's hear the options.
The options are A, standard deviation normalization, B, cosine similarity measurement, C, reciprocal rank fusion, or D, Euclidean distance calculation. I have to admit, I'm a bit confused here. If the keyword search gives a document a score of 8.5 and the semantic search gives that same document a score of 0.92, how do you mathematically combine an apple and an orange to get a unified ranking?
You don't. You actually don't combine the scores at all. The raw scores are totally irrelevant to the merging process.
Wait, really?
Yeah. The correct answer is C, reciprocal rank fusion, commonly known as RRF.
So it bypasses the conflicting metrics entirely.
Exactly. RRF completely ignores the arbitrary scoring numbers. Instead, it looks strictly at the rank of the item on each respective list.
Oh, wow.
So if a document is ranked number 1 on the keyword list and ranked number 3 on the semantic list, RRF applies a mathematical formula that heavily rewards items that appear near the top of multiple lists. It basically fuses the results based on mutual consensus.
That is such an elegant solution to a messy problem.
It really is. And if we look at the distractors, A, standard deviation, is a statistical measure of variance, right? Not a merging algorithm. Interestingly, B, cosine similarity, and D, Euclidean distance, are the mathematical methods used inside the vector database to find the semantic matches in the first place.
Ah, so they generate the scores, they don't fuse the final lists.
Correct.
That brings us to our final hurdle. Blending search systems is one thing, but blending completely different data formats is the ultimate challenge.
Yeah, this is the cutting edge.
Question 10. A retail application stores both product descriptions and product images. You want to allow users to upload a photo from their phone and find database records that are visually similar, or type a text description to find matching images. What type of artificial intelligence model is required to generate embeddings for this unified search space?
Okay.
Options are A, standard tabular regression model, B, a localized time series forecasting model, C, a traditional natural language processing model, or D, a cross-modal or multimodal representation model.
The word unified in the prompt is the giveaway here. The only correct answer is D, a cross-modal or multimodal representation model.
I have to pause and ask about the underlying physics of this. How can a digital photograph of a shoe and the text word SHOE possibly exist in the exact same mathematical space. They're entirely different file types.
This is where the architecture becomes truly brilliant. A multimodal AI model is trained simultaneously on millions of pair examples, an image, and its corresponding text description.
Okay.
Through that massive training, it learns the underlying universal concept of a shoe. So when you pass an image through its vision encoder and the word through its text encoder, the model outputs vector embeddings that land in the exact same region of that high-dimensional space.
It extracts the abstract concept right out of the physical medium.
Precisely, which means you can seamlessly query a text vector directly against an image vector.
Mind-blowing. And the other options?
Option C, a traditional NLP model, only understands text. Option A, tabular regression, is for predicting continuous numbers on a spreadsheet. And option B, time series, is for forecasting things like stock prices over time. Only a multimodal model bridges the gap between different sensory inputs.
Thanks for joining us on the deep dive.